Section 5-7 starts with rational exponents. These are exponents that are fractions. Here we have a definition of a base raised to a fractional exponent. If b is any real number and n is greater than 1, then b to the 1 over n simply is the nth root of b. So if we look at these two examples, 36 to the 1/2 is the same thing as taking the square root of 36, and 64 to the 1/3 is the same thing as the cube root of 64. Here we have a slight difference. We have 49 to the negative 1/2. Here we need to take care of that negative first by making it 1 over 49, all raised to the 1/2. Then we can take the square root. In number 4, here we have 1 over 8 to the negative 1/3. Again, we need to take care of moving the numerator to the bottom and the denominator to the top because of that negative, and changing the exponent to a positive. 8 over 1 can simply be written as 8, and now we take the cube root of 8. If we have a base raised to an exponent that's a fraction with a different numerator than 1, this is what will happen. Here we have a definition: b to the m over n equals the nth root of b to the m, or the nth root of b all raised to the m power. In other words, we could take the nth root first and then raise something to a power, or we could raise something to a power and then take the nth root. It sometimes is easier one way or the other, so it's nice to have both options. So we'll look here at a specific example. There are 3 ways to write a rational number. We can write it with a rational exponent or a fractional exponent. We can write it with the root of the power, or we can write it as the root to a power. So here are 3 examples. In the first one, this is easier to take the square root of 36 first and then cube it. And that's a 2/16. It's been cut off a little bit. And then in number 2, in this particular case, it's easier to take the cube root of 27 first and then raise it to the 4th power. And this is 81. And in the next one, we'll take the 4th root of 81 and then cube it. And our answer is 27. The next part of this section is called simplifying expressions. In order to simplify an expression, we have some things we have to fulfill. We can have no negative exponents, no fractional exponents in the denominator. Remember that a fractional exponent means a radical, and we can't have radicals in the denominator. No complex fractions, which simply means a fraction within a fraction. And the index, or the root, of any remaining radical is the least possible number. So let's look at some examples. And again, I apologize for the way this is translating to the Mac. But we have 4 to the 1/3 times a to the 1/2 times b to the 5/6. We'll want to get each of these exponents as a common denominator so that we can use that common denominator as our index or our root. So you can see here we've turned the 1/3 into 2/6 and the 1/2 into 3/6. So everything is in sixths. Then we can rewrite it as the 6th root of 4 squared times the 6th root of a cubed times the 6th root of b to the 5th. Using the product rule, we can put them all under the 6th root, and we can simplify the 4 squared. In this example, we have w to the negative 4/5, and just like a previous example, we need to take care of the negative first. Then we can rewrite it as 1 to the 4/5 over w to the 4/5. and obviously 1 to any power or root is going to be 1. Now, we need to rationalize the denominator. W to the 4/5 is a fractional exponent, which suggests that it's a radical. And anytime we have a radical in the denominator, we need to rationalize. So in this particular case, when we have a fractional exponent, we rationalize by creating an integer exponent. Remember, when you multiply bases, you add your exponents. So we're going to multiply both the top and the bottom, or the numerator and the denominator, by W to the 1/5, so that when we add the exponents in the denominator, we get a whole number or integer exponent. And then we will rewrite that numerator as the 5th root of W. Here, we're given the 10th root of 32 over the 8th root of 4. So we'll rewrite those as fractional exponents, and then we'll look at the bases. And again, we're trying to get like radicals or like denominators. So we'll start by trying to get like bases so that we can do some subtracting or adding when we divide. So 32 is actually 2 to the 5th. And 4 is obviously 2 squared. That allows us to have the same bases. And anytime we have a power to a power, we multiply first. So this simplifies to 2 to the 5/10 over 2 to the 2/8. Now, when we divide, first we'll simplify those fractions, and then subtract them, because we're dividing like bases. 2 to a power over 2 to a power allows us to do 2 to the 1/2 minus 1/4. Then we will get the 1/2 to have a like denominator and calculate, and then rewrite as a radical. Here's one that's a little more complicated. We don't have a monomial in the denominator here, so we're going to have to multiply by its conjugate. Remember, that simply means we're going to change that subtraction in the denominator to a plus, and then we'll multiply. Don't forget the shortcut. We take the first term in the denominator and square it, and subtract the square of the second term. We could also use FOIL if we don't remember that shortcut. So that leaves us with m minus 1 in the denominator, and 1 times m to the 1/2 plus 1 gives us m to the 1/2 plus 1. Then we would rewrite m to the 1/2 as the square root of m, and that is our final answer.